Hi guys, this is Chef Jin Academy. Welcome to this channel. In this video, I'm going to be showing you how you can analyze 2D frames such as this 3 example using F2. F2 is a two-dimensional structural analysis tool that is used to analyze beams, frames, and trusses. In my previous video, I've made a video on introduction to F2 and I've also shown you in that video how to analyze beam. You can check out the description of this video or check the top right corner of this video. So let's start. So the first one we are going to be working with is this example. This is a frame. We have a slanted member and an horizontal member, and we have about 3 nodes that we need to establish. We have 2 loads acting on it. We have a concentrated load and a uniformly distributed load. So let's head over to F2 to start this. So the first thing we have to do is to establish the first point. So let's take our point 1 as 0, 0. So what we have to do is come to the keyboard mode and then click on node. Then we establish the first node as 0, 0. So this is our first node here. So then to make things easier, let us check the grid so that we can work with the grid line and make the grid to be at 1 meters, because what we have here is 1.5. So let's make the grid to be at 0.5, 0.5. So now we've established the first node. To establish the second node, since this is 0, 0, the third node is the next easiest thing to establish. So you can see that this node is at 3 meters from A on the horizontal and 4 meters from A on the vertical. So we can use the same thing. Click on node, then on the horizontal, which is X, we put 3 meters, on the vertical we put 4 meters, and say okay. So this is the third node. Then the fourth node is also easy to establish. It is 8 meters from A along the horizontal and 4 meters from A along the vertical. So you can do the same thing, 8 meters here and 4 meters along the vertical, then you click OK. So now we can now join the members together by unchecking the keyboard node and clicking the insert member, then insert the members this way. So this is a simple way of establishing the frame. So the next thing we have to do is to establish the node here. To establish that, since this is at halfway from A, which is, from A to B is 3 meters, and this concentrated load, which is the second node, is halfway. So that means it's going to be 1.5, and along the vertical is going to be 2. So we can do the same thing. Click on node, then click on insert node, then the vertical is 1.5, the horizontal is 2. Since it is halfway, then you click OK. So you can see the node has been inserted. Then you have to be sure that the node is on this grid line. So now that we've established that, the next thing we have to do is to input the support. So, but before we input the support in F2, you first of all need to define a material property. Though, depending on the kind of frames you are analyzing, the material property can also influence the analysis. But in this case, we are just going to define a concrete section and make sure that the frame have the same sections. So we have to come to create a new parameter. Then we give it a name. Let's just say concrete. Then we change this to concrete isotropic, and then we say done. Then we just apply this to all current member in the model. That has been applied. So the next thing we have to do is come to section property. Then we define a new section property. So let's go with circle in this example. Then let's give it a name. Let's say concrete circle. Then you click on done. Then all you have to do is just to define the diameter of the circle. So let's say 200 millimeters. Let's just use this as an example, and then click on apply to all current member. So it has been applied as well. So the next thing to do now is to define the support. So in this example, we have 2 supports. We have a pin support at joint A, and we have a roller support at point C. So you can see that this frame is statically determinate. So all you have to do is this first node, we select it. For a pin support, that means we have to fix X and Y and allow for rotation. So since you do this, then you select apply support to selected node, and then you have your pin support. Then for roller support, select this node and you free the X direction, because a roller support is allowed to rotate, is allowed to move along the horizontal direction. So you just do apply to the node and then it's applied. The next thing you have to do is to define the load. So you come to nodal load so as to apply this 2 kilonewton 150 kilonewton load. So we come to define a new load. You just say P equals 150 kilonewton and we say done. Then you come to Fy. You have to make it negative so that the direction will be right. Then you click apply to selected node. Then this is the 150 node. The next thing we have to do is to apply the uniformly distributed load. So you come to uniform distributed load. Then you define it by creating a new load. So W in this case, the value of the uniform distributed load is 20 kilonewton meters. W equals 20 kilonewton per meters. Then you say done. Then you come to Fy minus 20 in order to define the load, and then you apply to selected member. So these are the two loads. We've correctly modeled this on F2. So with this, we can now determine the shear force diagram, the bending moment diagram, as well as the displacement. So, but before we do that, I'm sure the software will ask us to save. So let's just click on shear force. So this software will ask us to save. So let's name this as frame 1 and just click save. So once you do this, you can see this is the value of the shear force diagram. You can use this arrow button to increase the scale of the shear force and decrease it if you want. Then if you want to see the bending moment, you can just click on bending moment, and then it's going to display the bending moment to see the value. So let's say the values are small in the sense that you cannot view them very well. You can come to display, or you come to options, then you come to text size and put on large. So you can see this text size has increased, and then you can see them. So if you want to see the steps, if you want to see the values at 0.5 meters, so you can come to step and change the step to 0.5. Then you come to display, you come to step values, then you'll be able to see the value along the member. So you can see that the maximum bending moment, you can determine the maximum bending moment here. The maximum bending moment is around 234.4 kilonewton meters. So to see the displacement, so let's reduce this to this. I think this is much more reasonable. You can come to displacement and see the vertical displacement. So let's just remove the step values, so you can see the maximum vertical displacement. So the next thing we might want to look at is the reaction. So you can come to reaction, then you click on show reaction value. You can see the reaction here is 153.1 and the reaction here is also 96.1. So this is how you can model this frame on F2. So let us look at the second example. This example is much more simpler compared to the first one. You only have to define 4 nodes. So we have node A, we have node D, and we also have A, B, C, and D. So in order to model this, we just have to, let's take node A as our 0, 0. So let's come to F2 and click on new file. We want to create a new file. Then click on node. So let's create the first node at 0, 0, along the X to be 0, along the Y to be 0 as well. So the first node have been created. So let's create node B. Node B is along the X is 0, but it's 3 meters from A along the vertical direction. So you just have to do is change this to 3 meters and say okay. So this is the second node. Then the third node is node C, which is 9 meters from A along the horizontal and 3 meters from A along the vertical. So you change this to 9 meters and then you say okay. Then the last node is node D, which is about 1.5 meters from A, but in the negative direction, and 9 meters from A along the horizontal. So we have to change this to minus 1.5 because it's going down. Then you say okay. So all the node has been defined. So you can just click on this to bring all the node to your screen. So all we have to do now is to connect this node with a member. So you can do this by just clicking on member, and then you connect it with a member. So the next thing we have to do is to define the support. So let's say we have from the example, we have a roller support here, we have a pin support here. So you just have to come to, but before we define it, we have to establish different materials. So you come to create new model. Then let's just work with concrete again, and then change it to concrete isotropic. Then we come to apply to all members. Then we come to section property. Let's define a new section. Let's go with, in this case, let's go with a rectangular section, and then give it a name, concrete rec. You say done. Then you have to define the depth and the B of your section. So let's say the depth is 450, the B is 230. Then automatically the software will calculate A and also calculate AS and the value of the I. So we can just apply to all current section, so that because they are all the same. We come to the support condition. Under the support condition, we need a roller support and a fixed support. So this angle here is for pin support. So that means we need to fix X and Y and apply to current node, which is this. Then for this one, we only have to fix the Y direction and apply to this node. We only have one load here, which is a UDL of 30 kilonewton. But for this example, let's change this UDL to a triangular load. So what we have to do is come to linear load, which is this, and then give it a name. So let's say W for this load is 30 kilonewton per meter. Then you say done. But in this case, you need to input your I and your J. So all you have to input here is 30 kilonewton. Because it's a triangular load, so we just apply to this. But you have to make it negative so that the direction will be correct. So that means we've been able to define, to model this structure, this frame in F2. So all we have to do now is just to see the shear force diagram and also see the bending moment diagram. So you can come to this. So then this, let's name it as frame 2. Then click save. Then you can see the shear force diagram. You can increase it from here. Because this is a simply supported, this is a statically determinate frame. So that is why we have this. Then you can come to the bending moment. You see the bending moment diagram here. Then you can also come to the displacement to see the vertical displacement. You can come to display and you say show step value. You can put this to 1 meter, and then the value of the bending moment will be displayed. So let's play around with this model. Let's try to change the support. Instead of having a pin and a roller support, let's change it to a fixed support. So I select this member by clicking on this nose, and then I select the two node. Then we fix all three directions. Then you click on apply. So doing this, you can see that the shape of the bending moment and shear force is going to change. You can see the value around it. Then if you check the bending moment, you see the shape of the bending moment also changes accordingly. So this is how you can analyze different frames on F2. But let us look at the third example. The third example is a very practical example, because this is analysis of the connection between beam and column. So in a reinforced concrete, so let's assume this is a reinforced concrete structure. So the column 1 is the lower column, column 2 is the column in the upper floor, then we have these two beams connected to this column. In column analysis, most of the time you have to do this kind of analysis in order to determine the bending moment on the column, especially for column 1 in this example. So let us model this on F2. To model this, we have to define about 5 nodes. This is node 1 to 5. So let's come to F2. Let's define a new model by clicking on new. And then in this case, we can create material, or you can even create the model first. So making node 1 as our 0, 0 in this model, we come to the column section. Then we come to the keyboard mode. Then you click on node, you define your point 0, 0, then you click on OK. So the first node has been created. So let's create the second node. So let's assume that between the first floor and the second floor, the bottom of the column and the top of the beam is 3 meters. Let's assume that. And then the length of these two beams, beam 1 and beam 2, is 5 meters. The length of column 2 is also 3 meters. So that means node 2 is going to be 3 meters from A. Then the third node is going to be 6 meters from it. Then the next thing is you have to establish node 4. To establish node 4 is 3 meters from the bottom of column A along the vertical direction, and it is 5 meters along the horizontal direction. But in this case, it's going to be negative. So along the X, you say -5. And then along the Y, you say 3 meters. Then you say OK. You can see this is the first node. Then for the other one, it's just going to be +5 meters. Then you say OK as well. So we've been able to define all the nodes. So the next thing we have to do is just to connect this node with members. So you click on insert members. But in this case, we uncheck the keyboard mode, insert member, and then you insert your member this way. So practically most of the time we used to encourage a fixed support for all these 4 members, only in conditions where a pin support or a roller support will work. So because of that, you are going to define only a pin support. And then let's take the size of our column to be 300 by 300 for column 1 and column 2, and the size of our beam to be 300 by 450. Because in this example, the dimension of the column and the beam is going to affect the analysis. So that's why. So we come to material parameters. We define a new material. We say concrete, just like the way we've been doing. You can define any parameter. Then we select concrete isotropic and you say done. Then we apply it to all members because they are all concrete. Then you come to the section property. In this case, you are going to be defining 2 sections. So you come to create a new section. We create rectangular, and let's say this is for concrete column. You say done. Let's create another one. This is going to be concrete beam. Then you say done. So for the first one, which is concrete column, we put in the B and the D. So the B and D is both 300 millimeters. Then we apply it to the columns only. So we select this and this. You can hold the shift key to select 2 members at the same time. Then you click on apply current section to the selected member, so it has been selected. Then for the beams, you select the beams. Then you change this material to concrete beams. You change the size of the beam to 300 by 450, or let's use 300 by 600 in this case. And then you select apply current section to selected member, so it has been applied. So we've been able to define the section of our beam and column. The next thing we have to do is to define the support. So in this case, we have only fixed support. So we are going to apply fixed support to all the nodes. You can use the shift button to select more than one or two. Then you apply to selected node. You can see that the direction of the node here is wrong. So you can change, you select these two nodes and change this to 90 degrees. So then you click on apply to selected node, you can see it changes. So this is how you can model it. The next thing is to define the load. So because for this example, let's just take a load of, let's say 50 kilonewton meter as UDL, and let's say there is a concentrated load acting here. So we can just come here and say, okay, define this, and then come to UDL. So let's define a UDL of 50 acting along these two members. Most of the time the load might be different, but we can use the same load depending on the loading condition. So let's say W equals 50 kilonewton per meter as the UDL load. Then you say done. Then you can define the load 50. So let's apply it to only this member. Let's apply it to these two members at a go. And we just say apply to selected member. You see the load. So let's say we have a concentrated load in this region. So in order for you to define a concentrated load, all you have to do is let's on this grid. And because this is 5 meters, so this is 1 meter, 2 meter, 3 meter, 4 meter, 5 meter. So let's say the concentrated load is at 3 meter from here. Let's check the snap so that we can snap to this grid. So we insert a new load here. Since we have inserted a new load here, we can now define the concentrated load. So let's say the load is 2 meter for here as an example. So all you have to do now is uncheck the snap. Then you come to concentrated load. Let's say the concentrated load has a value of P equals 100 kilonewton. Then you click on done. Then you put the value of minus 100. Then you apply it to the selected members. So from this, we've been able to model the structure, the frame. The next thing for us to do is now to determine the shear force diagram, the bending moment diagram, as well as the displacement. And then we can now know the amount of moment that is being that our column is being subjected to, that is the lower column, which is column 1. To do that, all you have to do is come to shear force so that you can save it. So it's asking us to define a material for all members. Probably we've not defined materials. So come to material property. We have concrete. Then apply to all member. Then you can come here again. So let's say column beam system. Then you say save. Here you can see the shear force diagram. You can see the shear force along the beam. We have 189.8 here. We have minus 10. So you can use this to increase and decrease the value of the shear force along the beam. So if you want to see the axial compression as a result of this load, you can click on this axial force. You can see the axial force is 192, 192, 172 on the member. Then to see the bending moment, you click on this. So this is going to give you the value of the bending moment acting on the column. You can see the bending moment of the column is 21.1. So this is the bending moment on the column. For column 1, at the top of column 1 is 2.1, and at the top of column 2 is what? At the bottom of column 2 is 2.1. So let's say, for example, because this load is closely related, so that is why the moment on the column is very small. Let's delete one of the concentrated load by coming to load, or you can come to node. You can click on this. Let's remove this node, and we say delete, so the load goes away. Then we come to bending moment again. You can now see that the value of the bending moment increases. Or let's come to this member and remove one of the load. So let's say one part of the beam is loaded while the other ones was not loaded. So we can come to this, and then let's delete the load. Let us delete the uniformly distributed load, which is uniform load from selected member. So we removed it. So let's now define a new UDL. So let's say the UDL for this one is 15 instead of 50. So let's say W equals 15 kilonewton per meter. Then you say okay. Then you put a value of minus 15, and then you select the beam. Then you click on apply uniform load to this beam. So doing this, you can see that the load is no more uniform. So definitely we are going to see a significant high bending moment acting on the column. So if you come to bending moment now, you can see that the value of this bending moment has now changed to 10.4. So this is how you can analyze a beam column system, and even analyze any kind of frame using F2. If you like what I show you, you can hit the subscribe button and turn on the notification. Make sure you subscribe to this channel. I'm going to be making more videos on structural analysis and design. Thank you. See you in the next one.